Hey everybody, thanks for joining me. I'm really excited to be going through this and talking a little bit about doing machine learning in the cloud and the considerations around cost and performance and how we can better understand all the different resources we're using when we're doing machine learning in the cloud, as well as how we can kind of get the best performance out of our resources that we're going to be using. So I'm really excited to get us started and kind of we'll walk through a number of different kind of offerings in the cloud, as well as how you can utilize them more efficiently, effectively, and hope you find this useful. Let's dive in. Today we're gonna talk through kind of a couple of different aspects of your kind of typical machine learning workflow. I'm not sure why the words disappeared there on us. It's kind of funny. Okay. Um, so we got experimentation, right, when we're just kind of prototyping stuff, and that's usually using notebooks and things like that. Preparing the data, very important step here, and something that I think when you move your context into the cloud, there's some differences, there's some changes in terms of the mindset that you can make that will make your processing not only more performant but also more cost effective. Then, of course, there's the training. Everybody loves to talk about the training, but it's really just that one component. But getting it right can be really, really important, depending on the types of models you're using, the sizes of your data sets, and how those two and a number of other variables combine together. Once you have a model trained, it's not going to do anybody any good unless you're able to serve predictions with it. And so then we'll talk a bit about that component. There's a number of options now around how you can serve your model. And so making those decisions kind of consciously and with performance and cost in mind can really make a big difference. And then finally, there's orchestration and performance monitoring. These are kind of more up and coming topics. I think pipelines is probably going to be the big word that you'll see a lot about machine learning and data science in 2020 and beyond. As machine learning and data science practices mature, we'll see a move toward more and more traditional software engineering paradigms and approaches, and this merging of CI/CD and DevOps towards machine learning and applying some of those ideas there, I think will only continue to make the field a much more both production ready and production friendly situation, as well as make all our systems much more reliable. So with that, let's go on and talk a little bit about the experimentation phase, right? So this is usually when we are in Jupyter Notebooks, when we're in just kind of exploratory situations, okay? And so what we'll want to do is kind of talk through a couple of topics here around sampling your data, machine selection, creation, kind of curating the virtual machines that you'll be using in the cloud, as well as accelerators, our favorite topic sometimes, GPUs and such. So firstly, I want to step back and talk a little bit about, make sure we're all on the same page around what is AI Platform Notebooks. It's basically just a wrapper around running a Jupyter Notebook on a compute engine virtual machine. So Google Compute Engine is Google's kind of virtual machine or VM solution. So it's GCE VMs with a specific image that has a number of libraries installed, your traditional kind of pandas, NumPy, TensorFlow, Torch, etc. And then you can basically just run that out of the box and not have to worry about installation, setting it up, things like that. And so that can allow you to spin up a very kind of even set of images very quickly for your team, and know that they will not have kind of these installation and setup pains that are very common when you're making your own environment. The other component of it that's important to point out is that it is running Jupyter notebooks on the VM, but to access it, the team actually added what is called a reverse proxy in between your computer and the virtual machine that has the Jupyter Notebook server. And what that'll allow you to do is to actually go to a secured URL and access Jupyter Notebooks like it's local, which is like it's a cool thing, and they really did a nice job there, so that you don't have to manually. Before we would have had to manually port forward an SSH into the machine, and then in the URL it would show up as localhost. But here it actually will show up as a normal HTTPS URL. So the first point I want to talk about is sampling your data, right? A lot of times we have really big data sets, a lot of images, a lot of data. Sometimes they're small if we get lucky, right? But a lot of times for meaningful results, we need larger data sets. But when you're experimenting, you don't need the whole thing. And so that means you can take a slice of data from your larger data set and use that during experimentation. And so that'll give you a lot of flexibility when it comes to performance around this experimentation phase. So you won't have to wait for things, right? You won't have to wait for things to finish running. You can just kind of like be very nimble and agile in that way. And so that's my first kind of general tip around making sure that your data is set up so that it is easy to slice up, right? So whether that means you need to partition your files, change your directory structure, that can make a big difference. So with, as I mentioned earlier, Jupyter notebooks, AI platform notebooks are pretty straightforward to get started with. You literally kind of just click new instance and you can choose one right away, but there's also, it's easy to customize, so you can very easily choose your own kind of adventure, right? So you want to be smart about what kind of virtual machine you have backing your Jupyter notebook. Don't just be blind about it, right? You want to be smart with it. And so the first note here is that we want to make sure we select the machine type with the right kind of cost and performance trade-off. So Google Cloud allows you to basically pick and customize any machine you want, right? For those of you who may have like built your own computers before or kind of picked out hardware for your own servers, you know that typically we would select some CPU with some number of cores and some kind of performance, and then you would choose and go and purchase some amount of memory, some amount of RAM, and you install it in and you say great. But then what happens a week from now, a month from now, when you say, I need more memory, right? So then you go out to the store, or you need more, lo and behold, you need more compute, right? That's a real problem. But let's say just the memory piece. You go out and you get buy some memory, or you order it online, it shows up. You turn off your computer, you open up the box, you plug in another DIMM of the RAM, and now you have more memory, right? And then you start it all up again, make sure everything is visible and it's good. But that's like a sunk cost, basically. And so you can kind of avoid overpaying for resources, because usually you want like a bunch of RAM and then not really for a while, And so having that flexibility is part of the point of cloud, is being able to basically add CPUs and memory, and then importantly, take them away when you don't need them. That flexibility is one of the real kind of superpowers when it comes to using cloud resources. And so the other component, one more note I wanted to make here around Compute Engine, is you also want to avoid overpaying for underutilized resources. And one of the cool things that Compute Engine does is you can actually see here, I'll show you an example here. If I go to Compute Engine, you'll see that it will actually tell me that I can resize, change two of my virtual machines and save money, right? It will actually help me reduce my cost automatically. And so it's always looking at your usage and kind of thinking about, okay, what can we do to utilize these machines better? And if you're not utilizing them, it's better to size it down to be appropriate. It's the right size for the right job, basically, right? And someone else can use those resources, and they'll be happy to pay for that instead. And the final note I'll make here is that Compute Engine also has this concept of preemptible virtual machines. Now, people that I've talked to who really use preemptible VMs, they love it because it's shockingly less expensive, and you get the same performance. Now, you can't have your cake and eat it too. You do lose out on one thing, and that is the fact that the VMs can be what's called preempted. And what that word means is that if some other user comes along and says, I want to pay full price for this virtual machine, then you will be notified that you have been basically replaced. And so for experimentation, this can be a little bit tricky. But it's something worth keeping in mind, especially in later phases, when we have automated ways of kind of A, we're saving our data off the disk, and then B, we have automated ways of kind of shutting down gracefully and then starting back up in a new preemptible instance. And the cost on these is like, I want to say like 5 or 10x cheaper. It's crazy. So whenever we have an opportunity to use preemptible VMs, we pretty much should. Yeah. And then let's see, there was one other thing I wanted to talk about with the virtual machines and their selection and setup, but I'm blanking on it right now, so we'll come back to that. Okay, so the next point I want to talk about is accelerators, right? So GPUs are fairly straightforward to add and remove in AI platform notebooks. You can actually do it while it's turned on. You can do it live. So you can basically go and I think you can at least. Or was that? I might be thinking something. Maybe you can't. Don't quote me on that. But you can certainly easily add and remove GPUs and have multiple GPUs. And so you want to, think about your GPU usage and how many you want and per machine, multiple machines, things like that. But don't keep them on forever. When you don't need them, take them away. And I remember the thing I wanted to talk about earlier. Store your data somewhere else, right? And you want to think of these machines as ephemeral. Almost, that's the preemptible thing, right? Don't rely on the local disk that's attached to that compute instance. We want to make it so that the data and the code that you're writing, checking into source control, is easily accessible outside of that one machine. We should always operate under the assumption that your virtual machine might just poof, disappear. Okay? And so you want to do things that help you be able to A, share and collaborate, but also B, recover from any kind of situation where you might lose your compute, right? So we want to dissociate compute and storage, and this is one of the mindset shifts that need to happen as you move to the cloud, is that it's different. And so it gives us these extra flexibilities around things that we couldn't have done locally, right? We can't just separate our hard drive and compute. If our machine goes down and it corrupts the hard drive, oh my goodness, it'd be the worst. But in the cloud, you can store things in cloud storage, you can store things in file store, and have that be separated from the compute aspect of it, which means you can scale up and down the compute without worrying about the disk, which is really nice. And one final note would be that you can also monitor GPU metrics. There's a number of kind of pre-written scripts you can just take and use, right? Copy paste is definitely the secret of a lot of software engineering. So one final note I'll make about the compute side of things is that we have a kind of service called, not service, but it's in the cloud marketplace. There are deep learning VM images. These are the images that are loaded into AI platform notebooks that you choose from. But you can also access these images directly. Okay, the team just provides them. They're effectively open sourced, and they're free, and you can just use them. And moreover, they also have container images that correspond to those VM images, which means that you can know for sure that you are experimenting, right, in the VM, in the same environment that your code will see when you deploy it to a container-based orchestration platform like Kubernetes. So that type of standardization across VMs and containers is something that we're seeing across the board in the industry as well, where companies are realizing that creating your own ad hoc experimental playground environment doesn't lead to better results, precisely because of the fact that then when you move the code elsewhere, it doesn't work anymore. And so one solution, right, is to fix the environment rather than trying to fix the code. So that's experimentation. Okay, so we'll move on to talking about data preparation. And here I want to highlight BigQuery specifically. There's lots of ways to prepare your data in the cloud. Beyond BigQuery, other things I would consider that you should consider looking at are a number of services that start with the word data. There's data flow, data proc, and data prep. Okay, so those are some other services. I just want to say them up front so that you have them in your mind and you can kind of look at those if that's something that you'd be interested in. And those are kind of more just like raw data processing tools. BigQuery is a little unique, and partly because of the fact it combines storage and processing together. Now, not everybody's using BigQuery today. I think maybe it's worth looking at. And one of the tips I'll give here is like BigQuery is a large kind of SQL queryable columnar database, and oftentimes that leads people to say, well, it's a database, it's for storing data, why would I process and prepare my data there? BigQuery has grown up a lot. It's over 10 years now on the market. It just got its 10th birthday this year. And what it has now in terms of data processing abilities and capabilities are just so much greater than just a database. I'll give you some examples. Firstly, you can run SQL in BigQuery in a way that just is not really possible elsewhere, especially for larger data sets. The kind of performance you get because of the kind of the way it's implemented internally and the data shuffling gives you an ability to literally run processing queries on like a terabyte of data in 60 seconds. That was one of the first things I did when I first got to play with BigQuery. Someone showed me how you can take the Wikipedia data set and you can run a regex on all the Wikipedia articles and the edit histories, and it processed a terabyte of data in about 60 seconds. And I was just blown away because it upended my own conception of what was possible in terms of data read speeds, right? Like usually you can't even read a terabyte of data in anything close to 60 seconds. You would need way more than that to just like load it in, and to also then run a regex on it, count it up, and give me a total. Well, it was to count the number of instances of a word in Wikipedia, right? In that case, it was the word dinosaur, but that's a separate story. And so a lot of times for these large data preparation jobs, it's both easier, faster, and cheaper to just run it in BigQuery and then have that output as a separate table, as a view, whatever it may be. And it means that when more data comes in, you have a SQL query ready to go. And so try to get the data as pre-processed as possible within BigQuery as you prepare it for training. And so, yeah, in general, it's just a good thing to look into. I really encourage you to check that out. Secondly, I want to make sure you're using the right kind of client libraries. BigQuery is very performant inside itself, but maybe you're going to write some Python code that's going to talk to BigQuery and say, hey, run this query, run this SQL, and you have some automated system for that. And so I'll point out that you want to make sure you're using what's called the BigQuery Storage API. So you can actually make requests to pandas directly, request to BigQuery from pandas, but you want to make sure you set the parameter that ensures that you're using the Google BigQuery Storage API, and that will give you a much more performant read from there. And it doesn't change your cost, but it improves performance. And then on the TensorFlow side of things, there is a BigQuery client built into TensorFlow that you want to also make sure you're utilizing rather than just like the raw API. That'll give you a much more performant read when you're running your queries, because that's one of the things around using BigQuery outside of the UI is that you're going to have to then stream the data back to your client, which will take time. You're loading it into whatever environment you're in, so that could potentially incur costs as well based on where you're calling it from. The final note I'll make here is to partition your tables. So BigQuery has this interesting support of table partitioning. So let's say you are getting a lot of time series data. Make sure you partition your data, either by day, by week, by month. It depends on how much data you have coming in. But make each partition a reasonable size. That will keep the whole thing from getting too unwieldy, because the way BigQuery works is, as I mentioned, it's a columnar database. And what it will do is, unlike conventional kind of SQL databases, when you make a query for you want to, there's no indexes. So when you choose a specific column where ID equals X, ID equals 5, it will actually scan the entire column to find ID equals 5 because it's not indexed. And where it benefits is that it's not going to look at the other columns. So all the data is vertically stored rather than horizontally stored as rows. It's stored as columns. And so if you have a really big table, right, with a lot of rows, when you go and find something, it's going to scan the entire column all the way down. And so if you have a shorter table, each table scan becomes less expensive. Okay, so yes, so this is the note about BigQuery Client. This is kind of tying back to earlier when we were talking about the AI platform notebooks. One of the cool things is that they do include a BigQuery Magic in Jupyter Notebook that will allow you to much more cleanly express your SQL queries without having to wrap it in the actual call, and the results come out as a pandas data frame. So that's kind of nice. All right, so that's my little rant on data preparation. Let's move on now to training. And so training jobs are all about decisions. You have to make a lot of different decisions as you go through this process of setting up a training job. And making these choices will have pretty big ramifications on both your performance as well as the cost of your result. So let's talk a little bit about that. Firstly is choosing the right sized model, right? This is this isn't even about the compute. It's just what model are you going to use for your task? And choosing a larger model will have a lot of downstream effects. And so having the right sized model for the performance you're looking for is important. For example, you might be in a situation where you need really high accuracy. So then you're going to have to use a large model like Inception v4. But if you are perhaps deploying to mobile, instead of training a large model and then pruning it down, just train something like MobileNets and you'll just already be optimized for that size. So now let's talk a bit about machines. There's a lot to be said here. With regard to both the compute power, amount of RAM, whether or not you have GPUs, and then whether or not you use distributed. Okay, so those are the broadly how I think about the different criteria. And give you some examples, right? Obviously, deep learning situations with enough data will typically need GPUs. But sklearn and XGBoost won't. They don't utilize GPUs. And another example with more memory, you might use that for kind of a larger sklearn model. They oftentimes will eat up more RAM, so allocate more memory for those machines. And similarly with the distributed question, sklearn typically you want a single machine because it's not really multi-threaded, but with XGBoost, if you use the distributed XGBoost that is bundled in these machines, then you have the distributed option there for larger data sets. On the smaller data sets side of things, and when I say small, what I mean is if you can fit it in memory, then I consider that small. Now, with the cloud, you kind of have to change your conception of what does can fit into memory mean, because these machines can get pretty big. And so when you can have hundreds of gigs of memory, then it kind of changes the game around what you think of as like fits into memory. And so you could, with training, because it spins up a machine, runs your training job, and turns it all off for you, you can really spike up to really large machine sizes pretty effectively, and that can be really useful. So let's see. Another note I'll make is that when you are trying to scale your training job, scale up first. Get a larger CPU. Get more memory. Do that before you start scaling out and getting multiple machines. Because when you think about the physical aspect of a distributed system, distributed server system, it's connecting over the network, right? Yes, it's in the data center. They have really fast networks, but it's not going to come close to the speeds that you're going to get out of doubling your memory, right? You don't want to have two machines with the same amount of memory if you can have one machine with double that amount of memory. And so a lot of times you can just make the machine bigger rather than getting more machines. Let's see. One other note I'll make around distribution is that large data sets tend to utilize distribution better than smaller data sets. But hopefully that would already be happening, since for smaller data sets, you're only using one machine. With the distributed setups that AI platform training can use, you can choose parameter server sizes. So usually what you have is you have a primary node and then a lot of kind of worker nodes that are doing the computation of the gradients, and then you have a bunch of parameter servers that are all networked to those nodes. And these parameter servers, they're just computers, they're just VMs. And one of the tricky things here is that sometimes you can be a little bit bandwidth constrained with the sharing of all of those weight updates, especially for like a larger job. One subtlety that some folks aren't aware of around virtual machines is that the more CPU power you give it, you actually get associated network performance. and so if you give it more CPU, you basically want to over provision the CPU a little bit, even though it's a parameter server and shouldn't need that much compute. You'll get more memory. I mean, not memory, network bandwidth, and that is what you really want. With regard to the final note, this duration of training, there's a couple of flags that you should turn on. You want to use early stopping in your code. And AI platform training has a flag called max running time. So you want to make sure you utilize that as well. So that will help you control costs, because it'll limit how much, how long things run for. And you can also run hyperparameter tuning jobs. And so similarly there, you want to be smart about the trials you're running, like in terms of how many, as well as turning on early stopping, which is also just a flag. And one other note I'll make about hyperparameter tuning is that the way these tuning jobs work, they are not one and done. You can take your model, your training job, you can tune it to some degree, and you can say, stop it, before it's like done optimizing. That's fine. So you can choose a fairly low max runtime if you want. And then you can say, okay, got some results. It's not really done yet, but that's okay. I can run another tuning job, but I don't need to start from scratch again. I can actually set the previous one as the starting point. And so you don't really lose out on, there's no real cost to stopping early because you don't have to start over and do a longer one from scratch. You can just pick up where you left off and continue, which is, I think, a really nice thing. And it wasn't something that was always available, so a lot of folks aren't necessarily aware that this is an option. So I wanted to point that out. Okay, so after things are trained, we need to make predictions, folks, like that. And there's a couple of notes I want to make here. One is you can generally get away with, unless you're doing very high precision situations, you can serve in 16-bit floating point numbers instead of 32. So you lose out some precision, but it's okay. And there's a model optimization toolkit that TensorFlow now has, and so you should use that to quantize, prune, and like optimize the model that you'll be serving. And you can automate all of that once you know what you want to do, so that when you train up new models, this is just part of the release process, you know. And with prediction, just like with training, you're putting a model on a machine. And so you're going to want to think about what machine types you use and what machine types are available. So I actually have this link open here, so I want to show you some of the machine types here. So by default, it's going to choose this one, which is a mouthful. So I apologize for the long name, but it is just one CPU, 2 gigs of memory. It's nothing super impressive. And so you can choose other machine types. Now, it will, if you want to be able to do what's called scale to 0, you have to use one of these first two, okay? And you can see here we can have the ability to boost up to a quad-core machine. And so for more compute-intensive tasks like a large sklearn model, this might be appropriate. Now, if you want GPUs, as you can see here in this column, you have to, use the N1 type machine types. So all of these are what you might think of as standard compute engine machines. And so you can see the comparison here. They scale up much more rapidly with regard to the memory attached to the same number of CPUs. Right here we had 4 CPUs and 2 gigs of memory. And here we have same 4 CPUs, but 15 gigs of memory. So it's a lot more. It's a big difference. And you can kind of choose your lane here with regard to whether you want GPUs or not, whether you want to have more CPU, and whether you want to do what's called scale to 0. So when you want to scale to 0, what that means is when you don't have any users, it goes to nothing. But then when you have more users, you need to scale back up. So there's going to be a little bit of latency at the start, basically the cold start problem. So generally, if you have kind of a ongoing intelligent system that you've built that is serving responses in general to the web, you're not going to want to scale to 0. You might scale to a small number, but not to literally nothing. And you'll also notice that max model size is also constrained here. So in general, these models are good. These machines are good for smaller models, experimenting, trying things out. And then when you want to have something much more performant, much more kind of strong, you can move on to these. One final note I'll make here with regard to optimizing things is that you can also, let's see, before we go into that, I wanted to point out that for images, encode them as base 64. So when you send the data over the wire, over the network, images, sometimes you see examples and they encode them just as like arrays of numbers in JSON text, and it's just way too much. Don't do that. Base 64 encode them. They'll be much smaller packages. Your models will be more responsive. Everybody wins. It's less latency, less network bandwidth, faster performance and response. Like, it's great. So it takes a little work. Figure out basic C4 encoding. I mean, it's just use the libraries, obviously, but like just getting it to kind of work right, encode, decode, stuffing it into the JSON object, things like that. But once it's there, it's great. And it also means that you'll be able to serve more requests at once. So if you want, on your client side on the front end, you can take in multiple requests and then batch them all together and then send them down for prediction. And so as long as they're less than 1.5 megabytes in total, so this is more useful for like kind of tabular prediction, things like that, you can get them all at once. And this is still considered online prediction. Batch prediction is a separate mode where you're basically providing a file when you want to do predictions on that entire file, and yeah, it just returns you the file when the job is done. And so this is more useful when timing is not as concerned, but it's really, it's really good for doing batch jobs. You want to run a nightly job, no problem, and that can be very cost effective, right? So that's kind of what I'm trying to point out here, is that use online prediction, which is like the normal quote unquote one when we think about serving models, when you need it. If you don't need it, use batch prediction. It'll be a lot less cost, and the result is the same. And let's see, yes, delete unused model versions. So this is specifically for folks who are doing scaling that doesn't go to 0, which I think will be most kind of production use cases. If you're not scaling to 0, then your unused model versions will not scale to 0, and you're not using them, but they're still running. You don't need that. So you can get rid of unused model versions. You can still keep the models around, the underlying models, but the deployed model versions inside of Cloud Platform, that lingo, I'll show you what I mean here. So there's this concept of models, and then within a given model, there's kind of versions. So for example, like if I have, I don't know, I think I have a couple versions here, right? So you have different versions, and so you can delete these under the hood and just keep the one that's kind of still active, right? Your primary. Maybe you keep a backup one as well. Okay, so that's predictions and serving. Let's now move on to kind of pipelines and monitoring as we wrap up. AI platform pipelines is this kind of UI-based way to experiment and orchestrate your machine learning jobs from data collection and preparation all the way through training and deployment. If you want, you can really do quite a bit with it. It's very flexible, and it runs on Kubeflow pipelines, and you can basically you can create one-off or recurring runs, specify parameters of your choice. So it's pretty flexible in that way. You can create something that's kind of generic, and then you can basically make all of these runs of different pipelines of things. And so there's you can view the kind of process and progress as it's going, and this all is kind of handled for you. It's actually released now as kind of this pipelines product, and so you can have a pipelines kind of deployed very easily. I don't really know that much about Kubernetes, but it takes care of it for you. And so like I have different pipelines, you can have different experiments, and when you run them, it'll show. So you can see here, it'll show kind of the output, and it's a nice little interface for setting up your pipeline of processing and training. So I'm going to go back here and talk through a few of the principles here. One is that pipelines are just that, right? It's just a pipeline of steps. And because it's running on a Kubernetes cluster, it can, if you want, do the work kind of in place, right? You can have your pipeline literally be executing your training. and it's pulling the data into it. It's like running it on those containers. But I would recommend using managed services instead to handle all these things, and let pipelines just be kind of a layer over the top that's saying like, okay, now you go and process that data. Okay, you're done, push that over here. Okay, now you're going to work. You're going to do this thing, and I'm going to wait for you. And when you're done, so it's just an orchestration at the top level of just like pushing and pulling things, and just kind of keeping everybody happy. Basically doing what you would do manually otherwise, right? And so that sort of thing can be much more, shall we say, less demanding from like a coding perspective, as well as like simpler from an execution perspective. I generally favor keeping things on the simpler side rather than trying to make it unnecessarily complex. From a training standpoint, especially when you have a pipeline set up and you're basically updating models, retraining, and things like that, you can just incrementally train a model that you've already trained before, and new data has come in, right? This is kind of the point generally of pipelines, is you have new data constantly coming in, and your pipeline will basically trigger once in a while and cause your model to be updated. And so you want to be kind of training as an update from your previous models rather than starting over from scratch. It will improve training times, it will improve performance, everybody's happy. And during this process, though, make sure you do have a good evaluation data set that you are still using as a metric to compare against your model performance. So as new data comes in and you're training up these new models, it is possible, right, for your data to start, your model to start kind of floating away from the where you want the performance to be. So keep an eye on that, and sometimes you might need to basically start over, not literally start over, but like train a fresh model, right, with your data set, and not keep increments, because you can kind of wander off into the weeds, and then you can kind of reset a little by retraining the whole thing with the full data set. So we looked at these pieces here. Oh, I actually think I had one more point. Oh yes, when you're using AI platform pipelines, it does generate a fair number of artifacts, files, and obviously the model, but a lot of other things. So you make sure you go and clean that up periodically, just so it doesn't clutter up your storage. So I'll close with performance monitoring. Across GCP, there's a number of different tools, but for machine learning context specifically, there's going to be a lot of logs flying out of all these different services that you want to keep track of. So go over to cloud logging, get familiar with it, know where these are showing up, so that you'll debug better. Debugging is good. And take a look at cloud monitoring. It has Cloud Trace, Debugger, and Profiler, and you can use that to kind of get a better handle on your performance of your different systems. Now, if you're working in teams, or if you are administrating a larger deployment of cloud, and you have lots of different teams using these resources, and you want to provision them for different groups, and you want to have a mark on what is happening, you can put labels on them. They're just key value pairs that you can attach to resources. And so then you can identify and track the cost for, right? Because these labels actually show up in billing. So then you can see this team used this much resources, this team or this environment used some other, however you have it organized in your team or company. And so generally with these labels, there's arbitrary text, so don't make them unnecessarily complicated, right? Make them simple and useful for yourself, both kind of practically from how you implement it, as well as have it be meaningful kind of to the business. With regard to having all of these different services, and for the context of machine learning, because we're shuffling data around all the time, we're taking data and we're moving it here, we're pre-processing it, putting it to training, moving it to serving, put them all in one region. And if you want to use GPUs, you kind of need to put them all in one zone so that they will be in the same physical building, so that the GPUs can read the data as quickly as possible. And finally, I want to close by mentioning that Google Cloud has a number of discounts for sustained use. So if you are using a resource for a significant portion of a single month, you'll get sizable discounts on that overall cost. And that actually gets applied automatically. So if you're just, it'll just happen on its own as you're in the matter of you using it. Now you can get even more additional discounts if you already know that you're going to use a resource for, say, the whole month. You can get what's called a committed use discount, which get applied on top of the sustained use discounts if you commit to using a specific amount of resources like memory and RAM and GPUs and things like that. And so you can request these discounts basically in advance. So the one is post and one is pre, right? If you know you're going to get the discount, you can get even additional discount because then GCP can pre-provision that resource. It is more cost effective for them too. So yeah, for predictable steady state workloads that, kind of, you can almost think of it as like at a baseline level, you're going to need at least this much. Committed use discount, perfect. And then on top of that, any spiking that you do, you'll just use. And so that's where kind of this serverless versus sustained use model comes into play. With a lot of these managed services, you can choose sometimes even between using just the one-off kind of usage versus having a sustained use discount. And so the pricing models differ based on what you want to do. Like even BigQuery, they have flat rate pricing versus like a per query pricing. So with that, I'll wrap it up there. I want to call out the fact that I didn't come up with all of these myself. Much of this presentation was based on a really helpful kind of solution guide and has a lot more details and links about kind of optimizing for machine learning performance and cost on Google Cloud. And so if you're ready to dive into this more and really get hands-on with it, all the resources and links kind of that you could really hope to play around with are there. And in addition, cloud.google.com/ml has your one-stop shop for all the machine learning on Google Cloud. As for myself, I have a couple of video-based resources that I'll point you to. One is AI Adventures. It's a video series. Kind of we explore the art, science, and tools of machine learning, and that's been something I've been doing for the last couple of years. It's been a lot of fun. And more recently, during these pandemic months, I've been playing around with, we've started kind of a more casual YouTube channel for kind of live streams and discussions called Adventures in the Cloud. And so you can check that out. That's a little broader. There's definitely a good amount of AI and ML stuff, but we cover a slightly broader spectrum of things. And I've been kind of experimenting with Kubernetes on there and things like that. So yeah, thanks so much for joining me today. You can find me on Twitter at Yufeng, and let me know what you thought if you have questions. And until next time, I guess. Thanks so much, and be safe. Take care, and I'll sign off for now.